Lesson 114 lecture. So this is on graphs of factored polynomial functions. So I think we already know a few things about functions. I think we already learned, I don't know if we learned this. I want to say something about this though. Sometimes I write these functions on the board and I ask you, what are they? Now, I'm not going to write all the ones maybe I don't write stuff on the board too much anymore. But this thing, you might recognize this as x squared. And then this thing, maybe some of you would recognize this. I think that some of you told me you don't recognize this. But this is x cubed. This is a cubic. And then I think we had the conversation a while back. What could that possibly be? Well, it turns out that could be x to the fourth or some, translation of it. Let's do a couple more. This is just a review because I think we already talked about stuff like this. So notice there's a little pattern here. This thing has one little, turning point, you could say, and it's squared, right? It has one little bendy part. This has, this is a flex point. We'll talk about that in a second. But this kind of curves once and then it curves again. So it's got two little bendy places. And it's x cubed. This one, 1, 2, 3 little turning points, and it's x to the fourth. See how the number of turning points is one less than the power? This one's kind of weird because it's the way I drew it. I should have drawn you a nicer one like that, right? Then it'd be very easy to tell, right? That's just a flex point right there, but this could also be a cubic right here. Okay, that's one. This has how many turning points, or how many places does it change directions? 1, 2, 3, 4, and do you get the idea? And then I'll do one more, x to the sixth. This one would go something like that, right? 3, 4, 5. And we noticed stuff about the end behavior. I think we've talked about end behavior before. If it's got a even exponent, then the two, the arrows, the end behavior is going to be the same as x goes to positive and negative infinity. They're basically the arrows are going to point in the same direction. Okay, if we have a even exponent, see all the ones with the even exponent, how the arrows point in, they both point up, and then how these ones they point in the opposite direction when it's odd exponent. And I could even go into more detail. I could say, well, if I wanted to go x to the negative x to the fourth, it would go this way, right? It would just flip upside down because when we put a negative out there, it reflects across the y-axis. So those are just some things that I think we already know, and some things that we'll want to keep in mind as we learn this new part. So so that's what they're saying about the turning points. We begin by considering the number of turning points, the sign of the highest degree, because the sign of the highest degree, if it's positive, it'll, like this quartic, if it's positive, the two endpoints they'll point up, but if this were negative, they'll point down. So that's what they mean by the sign of the highest degree. And then the zeros are where they cross the x-axis, and we can find those out by factoring, and we've been doing that before. And so they're telling you that a turning point is a hump, like turning point, turning point, turning point. We can also call them a local max or a local min. This is in bold. This is what I just told you about It says the turning point theorem tells us that a polynomial has fewer turning points than the degree. So if it's like x squared, it's going to be one fewer. I mean, if it's second degree, the most it can have is one turning point. If it's third degree, oh, you can't see what I'm doing. If it's third degree, the most it can have is 2 turning points. Fourth degree, it can have 1, 2, 3 turning points. Sometimes it doesn't. Sometimes stuff happens to kind of flatten it out, and it doesn't have as many turning points. So you should probably read this stuff, but I think, you know, I've kind of summed it up a little bit for you. And then, what's the dominant term? So, dominant terms are whatever has the highest degree on it, because in the end, whatever has the highest degree on it, as x goes into infinity or negative infinity, it's going to like dominate the graph. So basically, if you have something in the highest degree is a cubic, its shape is going to be somewhat like a cubic, even though you have a square and some other stuff. The highest degree is going to dominate. Okay, so that's kind of what that's talking about. Sign of the coefficient. Yeah, we want to look at the sign of the highest degree to see if the two, if it's going to be, you know, upward like if it's a parabola, is it upward facing or downward facing? Because that tells us if it gets reflected over the axis, the x-axis or not. Flex points. Sometimes it doesn't really look like a turning point. It's more of a flex point, like that cubic I showed you earlier. Like this could be a cubic, and it's just got the flex point, or it can just, you know, it's got 2 turning points. What's the definition of a flex point? A flex point is an inflection point. We just kind of shorten it and say flex point. And it's saying right here that they're difficult to formally define. There are 2 points on the graph where the graph switches from being face up or concave up to being concave down. Okay, so like this part of the graph is kind of concave up, like it's like a cup, and then this one is gone concave down. So that's a flex point. Okay, and then here's a lot of here's a lot of quartics. The quartic, it can have 3 turning points. They don't have to be all nice and perfect like that. They can look really different, right? And this one, you can't even tell. This one, they're saying this is a quartic, but it's just the turning points are straightened out. Okay. Got 2 more minutes to talk about this. This must be a negative quartic, right? Because it's got 1, 2, 3 turning points, so it must be to the 4th power, and they're pointing down, so it's probably a negative quartic right there. What else? This is really interesting. I always find the vertex of a parabola by going x equals negative b over 2a, because somebody just taught me that. That's kind of part of the quadratic formula too. That's the part that's not in the radical, right? But I didn't know that it worked for all the other, you know, for the cubics and the quartics and the quintics. You can actually find the average of all the roots. So I wrote cool in my book. I wrote cool next to it because I thought this was really interesting. I'll admit that I never used this, but it is very interesting. It can help you find the center of a graph if you're just trying to graph something by hand. So it's negative b over, then like if it was a cubic, it would be 3a. And we already know that, so it's easy to remember if you know the negative b over 2a is how you can find the vertex of a parabola. Negative b, if it's a quartic, it would be negative b over 4a. And what's the a and the b? Those are just like the coefficients of the terms when they're written in descending order of exponent. Okay, so what are we going to do? Zero factor theorem, I think you already know that. We use it all the time. If you can set 2 factors equal to 0, that's a really good help in solving them. So that, like, we do this all the time. We go, oh, we have all these factors, so x can be 4, x is negative 3, and x is 15, right? So these help us find where the graph crosses the x-axis. And I think the rest of it, so I'm going to end this video and then I'm going to do some problems for you in the next video.